Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A Level Chemistry Unit 5 for June 2022. This is the Part 2 video. I already did the Part 1 and I'll do the Part 3 and put both below the description box. So let's begin. Question 12 says, this question is about 2-ethanol aminobenzoic acid. Crystals of this compound emit flashes of light when crushed. 2-ethanol aminobenzoic acid can be synthesized using benzene as the starting material, as we can see here. So this is benzene, and here we can see they're using an aluminum chloride catalyst and adding CH3Cl, giving us methylbenzene, and so on. So this flow chart or process leading to the formation of 2-ethanol aminobenzoic acid. So they say, a student proposed the mechanism for step 1. Step 1, conversion of that from that. This has to be an electrophilic substitution reaction whereby the electrophile is going to come and substitute the hydrogen. So here they say the proposed mechanism is CH3Cl plus AlCl3, giving us this electrophile and that. And then they say identify 2 errors in the mechanism by circling them. When I look at this mechanism here, that is where the errors are. We see that the arrow is moving from the other side, from the electrophile to the ring, which is wrong. The arrow should be showing the movement of electrons. So if the arrow is in that manner, it means the electrons are moving from the electrophile to the ring, which is wrong. An electrophile is an electron deficient species, so it means it is lacking electrons and it wants to gain them, meaning the electrons should be moving from the ring towards the electrophile, as you can see in red here. So that should be the correct way, and that is wrong. So I circled one wrong thing, that one you can see there. The next one is this one here. When this bond is being reformed, it should be a double arrow, not a single arrow, meaning 2 electrons or a pair of electrons from the carbon-hydrogen bond, is being returned to the ring in order to reform the ring, and that is why it should be moving in that manner, and it should be a double arrow like that. When I say double arrow, I mean it should be pointing like that, or double-headed arrow like that. Okay. So those are the 2 errors I have identified. Let's continue to the next page. Here they say, state how the errors you have identified in A1 should be corrected, and they want you to justify your answer in terms of the structures involved. Like I've already explained to you, I say the arrow should be from the ring towards the CH3. Remember, the ring is electron rich, and this is the electrophile that is electron deficient. So the electron rich ring should give electrons to the electron deficient electrophile. I say it because CH3 plus is the electrophile, is electron deficient, and the ring is electron rich. Next, I say the arrow from the carbon-hydrogen bond should be a double-headed arrow, since both electrons from that bond are donated to the ring in order for the ring to be completed. The next question says, give a reason why it is important to keep the temperature below 30 degrees Celsius in step 2. I want us to go back to step 2 so that we see what is happening there. Step 2 is a reaction, this is a nitration reaction, so concentrated nitric acid, concentrated sulfuric acid are reacting with this one here to convert it to that. So guys, when you observe this is a methylbenzene. Because the methyl group is electron donating, a methylbenzene is more reactive with electrophiles in comparison to benzene. So that means if this temperature is really high, this methylbenzene is going to be extremely reactive and further substitutions could occur. So there could be a 2 nitro, there could be a 4 nitro, and so on. But in this case, we want to limit or minimize the substitution. So the temperature has to be lower so that we prevent further substitution and production of other nitro compounds that are not our intended compound. So let's go back, we see my answer. I said, to prevent further electrophilic substitutions by other nitro groups, the methylbenzene is easily attacked by electrophiles than benzene because the methyl group on the methylbenzene is electron releasing, or you would say is electron donating. Part C says, say the type of reaction in step 3. Let us go back a bit here. Step 3 is this one here. This is an oxidation reaction. We are using potassium manganate 7. Yep, that is an oxidation reaction. So the answer is oxidation. This says identify by name or formula the reagents needed for step 4. Again, I'm sorry, I gotta take you back. Step 4 is this one here. In step 4, we see a nitro is being converted into an amino. That means hydrogen has to be provided or reduction has to occur. This step here is reduction, and the things we need are tin in the presence of concentrated HCl. So those are the things we need here to convert that functional group into that functional group. So I said here, tin and concentrated hydrochloric acid. Moving on. Here they say explain how the structures of ethanol chloride that in compound A enable them to react, forming 2-ethanol aminobenzoic acid in step 5. Let us go back here. They are looking at this reaction, how that and that are going to react in order to produce the final product. So a reaction between this one here, this one and that. If you look at this compound here, it's CH3COCl. This one here, this carbon here is electron deficient, and that is partially minus. So there is a polarity within this bond, yet this nitrogen has a lone pair of electrons. So the electron deficient carbon, this one here at the center, that is going to receive electrons from the electron rich nitrogen, and that is going to initiate the reaction as this one here goes away. So that is where I'm going to begin my explanation from. So let's go back and see what I wrote. I said, let's see, the carbonyl carbon, that carbonyl carbon in this is electron deficient. So here I showed you electron deficient means this carbon is partially positive and that is partially negative. So the partially positive one is electron deficient. Then I said, however, the nitrogen on NH2 has a lone pair of electrons. Again, I showed you the lone pair there. And then the lone pair of electrons is donated to the electron deficient carbon atom, forming a dative covalent bond. And when that occurs, the carbon-chlorine bond breaks as the Cl atom takes the bond pair of electrons from the carbon-chlorine bond, becoming a chloride. So chlorine becomes a chloride, and then the NH2 is going to attach onto the carbon but with the formation of a dative covalent bond. The next part F says calculate the volume of benzene required to form 5.92 grams of 2-ethanol aminobenzoic acid, assuming the overall yield for this synthesis is 28.2%. They want you to give your answer to an appropriate number of significant figures. So here I began by looking at the moles of 2-ethanol aminobenzoic acid. Since we have the mass and we know the molar mass, or you could calculate the molar mass, the number of moles is going to be mass divided by molar mass, which is 3.3073 times 10 power negative 2 mole. Those are the number of moles of the product. Using the mass that is obtained, I can be able to find the theoretical mass or theoretical moles. So I know the number of moles. I'm not going to find the theoretical moles using the percentage yield I'm given. Those theoretical moles are for benzene. So I say percentage yield is actual moles divided by the theoretical moles times 100. This is the moles I have are here. Remember this, the number of moles of these to benzene, the ratio is 1:1. So the moles of benzene are going to be exactly that. However, those are actual moles. So the theoretical moles will be number of moles. We can see these ones here, the actual moles divided by the percentage yield times 100, giving me that. These are the theoretical moles of benzene. Now, since I have the theoretical moles of benzene, or the moles of benzene that will be required, so I can be able to find the mass of benzene that will be required by multiplying the moles of benzene by the molar mass of benzene. Molar mass of benzene is 78, so 78 times that gives me 9.1478. I can put grams here because this is mass. And then finally, I want to find the volume of benzene. Since I'm given the density, I have calculated the mass. I can be able to find the volume since volume is equal to mass divided by the density, which is that mass by the density. I get 10.407. Since my answer is supposed to be in appropriate significant figures, I have to look, when they say appropriate significant figures, it means look at the question and see how many significant figures have they been using. They are all using 3 significant figures, so stick with that. I say 10.4 centimeters cubed. That is again 3 significant figures. So this brings me to the end of question 12. Let's continue to question 13. Question 13 says, compare and contrast the reactions in aqueous solution of nickel-2 sulfate with sodium hydroxide and with ammonia. And they say for each reaction include what would be seen, that is your observation, any color changes and so on. And then also include the equation. For these, state symbols are not required, and also include the type of reaction. Is it a ligand substitution reaction? Is it a deprotonation reaction? And so on. So since this is a compare and contrast, I began with similarities. Similarities for when nickel-2 sulfate reacts with both. So I said when nickel-2 sulfate reacts with both sodium hydroxide and ammonia, deprotonation reactions take place. So the type of reaction will be deprotonation, and when that occurs, green precipitates are initially formed. So next, I wrote the equations for the reaction. Here we can see hexaquanickel-2 reacting with sodium hydroxide. We get a complex as well as water. And on this side, hexaquanickel-2 reacts with ammonia. We get the same complex that we got here, which is a green precipitate. And then on the other side, we get 2 ammonium ions. Next, on addition of excess ammonia, the green precipitate dissolves to form a deep blue solution. So this is a difference because this will not occur when you add excess sodium hydroxide, while no observable change occurs with excess sodium hydroxide. So this is the difference between the two. Also, the reaction with excess ammonia is a ligand exchange reaction, as we can see here. In that case, if you added the excess ammonia to the hexaquanickel-2 plus, all the water ligands are going to be substituted by ammonia ligands, as you can see here in the product. So all the ligands are going to be ammonia and water ligands are going to be observed the other side. Now there is a situation if a student wrote the complex like nickel, H2O, 4, or H2. If this was the complex the student wrote and they added ammonia, then it means, again, we're going to see all the ligands going to be substituted. We will get an I, an H3, 6, like that. Plus, you would have 2OH, and then you would have plus 4H2O. Again, that would be a ligand substitution reaction, whereby all the ligands have been substituted, and we have only ammonia ligands present, and that will be a deep blue solution. So here, this brings us to the end of question 13. Let us continue to question 14. Question 14, a compound Q is a pale yellow liquid that is the main constituent of cinnamon oil. Q contains the elements carbon, hydrogen, and oxygen only. There is a complete combustion of 6.02 grams of Q produces 18.07 grams of carbon dioxide and 3.30 grams of water. They want you to determine the empirical formula of Q. To determine the empirical formula, I began by finding the mass of carbon, mass of hydrogen, and mass of oxygen using the given masses of water as well as carbon dioxide. So to find the mass of carbon should be 12 divided by 44 times the mass of carbon dioxide. That is the mass of carbon. To find the mass of hydrogen, I say 2/18 times the mass of water, and that will give us the mass of hydrogen. So the mass of oxygen should be this total mass, that plus that, subtracted from 6.02. So it should be 6.02 minus the total of the two, which gave me 0.72513 grams of oxygen. Then I went to my table, element, carbon, hydrogen, and oxygen. I found the moles of each. Moles of carbon should be the mass of carbon divided by 12, which gave me those moles. Moles of hydrogen should be the mass of hydrogen divided by 1. 1 is the atomic mass, which gave me that. And the moles of oxygen should be the mass of oxygen divided by the atomic mass of oxygen, which gave me that. Then, after finding the number of moles, I had to find the mole ratio. We find the mole ratio by dividing through by the smallest number of moles. If you look at that, and that is the smallest number of moles. So divide everything by that, which for this case, it gave me 9.06. Here I got 8.09. And there I got 1.00. And rounding it off, I got a 9 to 8 to 1, meaning the empirical formula has to be carbon 9, hydrogen 8, oxygen 1, as we can see here. That is my answer. Moving on, they say, tests on samples of Q show that it burns in air with a sooty flame. If an organic compound burns in air with a sooty flame, it means it has a high carbon to hydrogen ratio, meaning it could be an alkene or it could be an aromatic ene, like an arene. The next they say it forms an orange precipitate with Brady's reagent. Brady's reagent is used to test for presence of carbonyl compounds, and if an orange precipitate is observed, then we can confirm that it's a carbonyl compound. So it means Q is a carbonyl compound. Then they go on to say that it forms a silver precipitate with Tollen's reagent. If something forms a silver precipitate with Tollen's reagent, then it is an aldehyde. So we can establish that Q, which is an aromatic compound, is an aldehyde and not a ketone. Next, they say it decolorizes bromine water. If something decolorizes bromine water, you could think it's a phenol, or somebody could think it's an alkene, meaning it has an aliphatic carbon-carbon double bond. However, we have already established that this is an aldehyde and there is only one oxygen, so there is no way it is a phenol. So we cancel that out and we can only confirm there is an aliphatic carbon-carbon double bond. Next, they say it exists as a pair of geometric isomers. That means every carbon in the carbon-carbon double bond has a higher priority group. Since the only groups we have are hydrogens, it means there is one hydrogen here and one hydrogen here, and then the others are going to be something else. So let's go to the next part of the question. It says, deduce the structure of Q, explaining how each piece of information supports your answer. So to me, this is my structure Q. I can see this is the aromatic part, or the arene, or the benzene ring. And then I can see this is my aldehyde part. Since I remain with two other carbons, this is going to be my carbon-carbon double bond because it cannot be here. If it's here, then I'll have so many bonds around carbon, which doesn't make sense. So this should be the only product or the only structure Q. So here I said, the very sooty flame indicates presence of a high carbon to hydrogen ratio, so Q is a benzene ring. Formation of an orange precipitate with 2,4-dinitrophenyl hydrazine indicates presence of a carbonyl compound. Formation of silver precipitates with Tollen's reagent indicates that Q is an aldehyde. And decolorization of bromine water indicates presence of a carbon-carbon double bond. Existence as a pair of geometric isomers shows that each carbon atom in the carbon-carbon double bond has only one hydrogen attached to it. And that is my conclusion. This brings us to the end of question 14. Let us continue to question 15. Question 15. This question is about transition metal compounds and their quantitative analysis. Part A says, potassium dichromate 6, that is present in very small amounts in cement to help increase the time for the cement to set. A 50-gram sample of cement was washed with portions of the ionized water to dissolve the potassium dichromate. Any insoluble residue was removed by filtration and the filtrate was transferred to a volumetric flask. The volume was made up to 100 centimeters cubed using 2 mole per decimeter cubed sulfuric acid. They continue to say 50 centimeters cubed of this solution was transferred to a conical flask and titrated with a solution of ammonium iron 2 sulfate, which is that, of concentration 3.24 times 10 power negative 4 mole per decimeter cubed. They're going to say the indicator N, phenyl arthuranylic acid, was used, which gave an intense red-violet color at the end point. The mean titer of the ammonium iron 2 sulfate was 10.90, so this is the volume used from the burette. Then they say the ionic equation for the redox reaction in the titration is as below. That is the redox reaction. They want you to state the color of each chromium species in the reaction. So this is diacromate 6, of course that is orange, and chromium 3 is going to be green. This is easy, everybody should remember that. Next they say, suggest a reason why an indicator is needed in this titration. Now we know this titration is going to have orange color this side and there will be a green color the other side due to chromium 3. The reason as to why we need an indicator is because a color transition from orange to green is going to be really hard to tell because they are such dark colors. So the color changes from orange to green at the end point. This change may not be clearly detected because the colors hard to tell. As orange is shifting to green, it will be hard for the observer to tell. But if there is an indicator that is going to give an intense red-violet color, then that is going to be observed as it's being formed in the solution where the titration is carried out. So let's continue. The next part, they say calculate the percentage by mass of potassium dichromate 6 in the cement sample. So to take you back here, I will begin with this information here. Remember, they gave me the number of moles as well as the volume, so I'm going to begin by looking at the number of moles. Remember, they gave you the concentration, they gave you the volume, so I will begin by calculating the number of moles of that. So let's go back here. Remember, each mole of this whole thing contains 1 mole of iron. So since they mixed ammonium iron to sulfate, it doesn't matter. 1 mole of ammonium iron to sulfate contains 1 mole of iron. So the moles of iron to sulfate and the moles of iron are going to be exactly the same. Moles of iron 2 equal to concentration times volume. What I did here is concentration is given times the volume. So the volume has to be divided by 1,000 to convert it to decimeters cubed. So the answer I got was 3.5316 times 10 power negative 6 moles. Those are moles of iron 2. Now, when we go back to the ionic equation, you can see the mole ratio between iron 2 to dichromate is 6:1. That means the moles of dichromate should be 1/6 times the moles of iron 2. Therefore, you can see what I did here. Moles of dichromate in the 50 centimeters cubed that was in the conical flask should be 1/6 times the moles of iron 2, which gives me 1/6 times that, and I got 5.886 times 10 power negative 7 moles. Those are the moles of dichromate in the 50 centimeters cubed. Now remember, the initial 50 grams of the cement, this one here, 50 grams of the cement sample, was not dissolved in 50 centimeters cubed, but it was dissolved in 100. And from this 100, we took the 50. So coming back here, it means I have to find the number of moles in the initial 100. To find the moles in 100, it should be 2 times the moles in the 50, which gives me 1.1772 times 10 power negative 6 mole. Now, since I have this, that is going to be the moles of the dichromate. I need to find the molar mass of the dichromate. Since this is the formula, you look at your periodic table, the molar mass is 294.2 gram per mole. Now, I'm going to use the number of moles and the molar mass to be able to find the mass. So mass of dichromate in 100 centimeters cubed should be the moles times the molar mass, which is that times that, and I got 3.4633 times 10 power negative 4 grams. And finally, percentage by mass should be the mass of the dichromate divided by the mass of the original cement sample times 100, and that gave me that as my answer. That is the percentage by mass. Let's continue. Here they say N-phenyl anthranilic acid has the structure shown. That is the structure. The solution used as an indicator was prepared by mixing 100 milligrams of this acid in 5 centimeters cubed of sodium hydroxide solution. The mixture was then diluted to 100 centimeters cubed with the ionized water. Explain why N-phenyl anthranilic acid is added to the sodium hydroxide solution before it is mixed with water in the preparation of this solution. If you look at this acid here, it of course is a carboxylic acid. And what happens when you react a carboxylic acid with sodium hydroxide? You form carboxylic salts. And everybody knows this is going to be a sodium carboxylate. A sodium carboxylate is more soluble than a carboxylic acid, or you would say salts of sodium are very soluble, and that is why it's going to be more soluble than the organic acid or its organic parent acid. So I said the sodium hydroxide reacts with a carboxylic group of the organic acid to form a carboxylate salt. This sodium salt is more soluble in water than the original organic acid. Part C says the concentration of chromium-6 in aqueous solution may also be determined using a colorimeter. They said on addition of 1,5-diphenyl carbazide or DPC to a solution of chromium-6 ions, an intensely colored octahedral complex forms. The formula of the complex is given here. They say the structure is shown, which you see here, minus the lone pairs. I put them there. Then they say describe how DPC is able to act as a bidentate ligand using your diagram to show the atoms involved. Now, when we look at this structure here, we can see there is a lone pair of electrons here, there, and there. Now, one of these lone pairs here and one of those is going to participate in the formation of the dative covalent bonds towards the cation in question. One of these is going to form one dative covalent bond, and one of these is going to form one dative covalent bond in order for these to be a bidentate ligand. So I said there are lone pairs of electrons on the nitrogen atoms. The lone pair on one of the nitrogen atoms on the left of the carbon-oxygen double bond, and a lone pair on one of the nitrogen to the right side of the carbon-oxygen bond forms a dative covalent bond of dative covalent bonds to the chromium ion. So the key thing is one of these forms a dative covalent bond to the chromium ion, and one of those forms a dative covalent bond to the chromium ion, and that is how this is going to act as a bidentate ligand. Moving on. Here they say the intense color of this complex is due to the transfer of electrons from the ligand to the chromium 6 ion. Suggest a possible reason why the color is not due to transfer of electrons between split d orbitals in the ion. They want you to refer to the electronic configuration of chromium 6 ion. Here I began by writing the configuration of chromium, which is argon 4s1 3d5. The configuration of chromium 6 is argon 4s0 3d0. This means that the orbitals do not have any electrons in them, and therefore there are no electrons for D to D transitions. That is why this is not possible. So any color is due to electrons being transferred from the ligands towards the chromium 6. Lastly, part D says the concentration of Nico2 ions can be determined by forming a complex with the ligand dimethyl glyoxime. We have it there, and this is a reaction involving that. They say explain why the formation of that dimethyl glyoxime complex is favored in terms of entropy. When they ask in terms of entropy, we have to look at the particles on the left side and the particles on the right side. If you see here, we have 2 plus 1, that means 5. The left side or the reactant side, we have 5 particles, yet at the product side, we have a total of 7 particles. That means if you check the entropy of the system or the S system, this is going to be positive. Or you can say the entropy of the system increases. So here I said the reactant side has 5 reacting particles, while the product side has 7 particles. The S system is positive, so the reaction is favored in the forward direction. That is why this reaction occurs. So this brings us to the end of question 15, as well as the end of the part 2 video of this paper. Thank you for being with us. Please do not forget to subscribe. See you in the next video. Bye-bye.